All right, now you can hear me. So please be seated. It's about time to start the first concurrency session of POPL. The first talk is going to be given by Aïna, Linn, Georges, called Data Race Freedom a la Mode. This is one of the recipients of a distinguished paper award this year, so the stage is yours.
All right, thank you so much. Hi everyone, thank you for coming. My name is Aïna, and today I'll be presenting our work on bringing data race freedom to OCaml. This has been joint work with a number of great collaborators from MPI, Jane Street, and Inria. So I think a lot of us here can agree that Rust is great. On the one hand, its powerful ownership type system provides fine-grained control over data, layout, and memory management. While on the other hand, it remains memory safe, and it even prevents data races. Now that being said, unfortunately, not everyone wants to program in Rust. So why is that? Well, it might be because of its lower-level style of programming. It can sometimes also be slightly annoying to fight with the borrow checker. And finally, it has a somewhat steep learning curve for programmers that are accustomed to automatic memory management, such as a garbage collector. So the first question we ask is, can we bring the benefits of Rust to a higher-level managed language like OCaml? And this question was tackled by Anton, Lorenzen, and others in this ICFP paper from last year titled Oxidizing OCaml with Modal Memory Management. And I will henceforth refer to this work as OXCaml. Okay, so OXCaml brings the following features to OCaml, namely stack allocation, meaning the programmer can control where some memory is allocated, and memory reuse, which allows programmers to reuse some memory for a different purpose. And this design has been very successful. In fact, it has been implemented at Jane Street. It's getting ready for deployment. And this really goes to show that this design is not just theoretical. Okay? It can really be implemented at scale. And has been done so in OCaml. So let me give some overview of OXCaml, as it will provide the foundation for our work. So in OXCaml, type declarations and typing judgments are decorated with a mode. Okay, it looks as follows. What is a mode? Roughly speaking, a mode provides additional information that influences the interpretation of a type. Now, more concretely, it means that programmers can annotate their types with one of the modes depicted here in 3 different lattices. And what's nice is that these modes can then be weakened towards the top element. So for example, a programmer can annotate a variable as unique, and then can then be weakened to alias. So all of these modes express something slightly different. So let's go through some examples. Right, so if x is marked as local, it means that x can only be used locally and may not escape its scope. If x is marked as unique, it exists uniquely and has not been aliased. And if x is marked as once, it can only be used once. For example, if x is a function, it can only be invoked that one time. So with these modes, OXCaml brings these features to OCaml. Okay, so it can use the local global axis to express stack allocation. And it uses aliased, unique, many once to express memory reuse. What's very impressive is that this design is completely backwards compatible. So that means that all existing OCaml code compiles, even with this new design, add the legacy mode, global many aliased. However, OXCaml does not consider concurrency. So we still have one nice feature from Rust that doesn't exist. And that's what we're going to do in this work. Okay, so we're going to expand the design of OXCaml to guarantee data race freedom in multi-core OCaml. And just like with OXCaml, we're going to remain backwards compatible. Okay, so more concretely, what would that look like? Let's see through an example what we will be able to do. Let's imagine we have a well-known OCaml data structure, a queue, that we want to share between 2 threads. Now, both of these threads will try to add an element to the queue, which will then create a data race since they're both trying to mutate it at the same time. So it's important that we protect the queue somehow. All right, so first step, well, let's imagine that we create some kind of lock, synchronization lock to wrap around the data structure. But the problem is this is still not enough. And the reason is, in languages like OCaml, you can freely alias any memory cell. So it's entirely possible to create this external alias y pointing to x, and thus circumventing the protections guaranteed by the lock. All right, so at this point, I want to take a sidebar and discuss, well, how does Rust manage this? How does Rust guarantee database freedom? And it does so by adhering to the aliasing XOR mutability principle, which means that values can either be aliased or mutable, but never both. Okay, so is it solved? Can we do the same? Well, not quite. So the problem is the aliasing XOR mutability principle doesn't work well for data structures with internal aliasing. Okay. So to be a bit more precise, let's imagine we have a double-ended queue. Well, the internal implementation of it has a lot of aliases. So if we need to adhere to this principle, it essentially means the two threads cannot mutate it. Yeah. Okay, so in Rust, what can be done is, well, you can use some APIs that allow you to safely mutate concurrent data structures with internal aliasing, such as the GhostCell API presented in SFP21. But the problem with APIs such as GhostCell, or the problem with GhostCell, is that it requires wrapping each node of this shared data structure with GhostCell wrappers. But that's not quite what we want. We want to share existing OCaml data structures cross-thread without having to re-implement them. All right, so the question is, how can we do this? And the key idea is going to, instead of using this principle, make this boundary around our queue a very harsh boundary, meaning we're going to create an encapsulated environment, which means no external aliases can exist, but we can do as many internal aliases as we want within the encapsulated region. So more concretely, what's our contributions? First, we present DRFcaml, a design that extends OXCaml to support concurrency. Now, DRFcaml statically prevents data races while remaining backwards compatible. However, it's going to be quite restrictive. So it also supports sharing existing OCaml data structures across threads. Okay, I'm going to explain how. And this whole design is proven sound in Rocq and Iris. What are the key ideas with the design? First, DRFcaml guarantees database freedom via two new mode axes called contention and portability. They are going to control how data can be shared across threads. Okay, next, DRFcaml supports mutation of shared data structures via two APIs, the capsule API and the reader-writer-lock API. And these are going to allow us to share existing data structures across threads without re-implementing them. Right, and I'm also happy to say that a design based on DRFcaml is actually also being rolled out at Jane Street. And in fact, you can all already play with it on an open repository. Okay. So let's get right to it. We are extending this, the mode axes with two new axes called contention and portability. And they're going to express how variables can be shared across threads. So to be more precise, if X is uncontended, it means it has not been shared between threads. If X is contended, it means it might have been shared across threads. And then for the next axis, if X is non-portable, it means it must not be shared across threads. While if it's portable, it can be shared across threads. Okay, now note I'm being very intentional with my use of verbs here. Okay, so there's a useful way to characterize these axes. The contention axis expresses something about the past of a variable. It expresses whether a variable has been shared, while the portability axis expresses something about the future. Can it be shared? Now let's see how these axes prevent data races. We're going to do this with an example. So we start out by allocating our queue, X. We then create a closure F that captures X and tries to mutate it. And we're going to run F in two different threads. Right, so first, I want to say, this program creates a data race. Right, two threads try to mutate X at the same time. So it's important that it's flagged as an error. And DRFcaml is going to do this with two rules. So first, mutable fields that are read from or written to must be uncontended. And second, functions that capture uncontended values are non-portable. Okay, so if we walk through this example, well, F is a function that captures X and mutates it. So X must be uncontended, the first rule. Thus, F is non-portable. But if we remember the rule for portability, if something is non-portable, you cannot share it across threads. Okay, so the error we get is that F is non-portable, but it's expected to be portable. All right, great. We have prevented data races. Now, problem. These rules are very restrictive. As you can see, with just this vanilla type system, you can't really share any mutable values across threads. Okay, so we need to fix this. And the answer is, we're going to present two APIs that will allow us to share mutable data structures across threads, the capsule API and the mutex API. Okay. And in the next couple of slides, I will present parts of both. First the capsule API, then the mutex API. Okay. So the capsule API really combines the full expressive power of both OXCaml and DRFcaml. It's going to use every mode accessed non-trivially. But simply put, a capsule is an encapsulated region associated with an abstract key type. Right, so let's see how keys are created. Keys are created by invoking key.create, where it creates this packed type. Okay, so a packed type is essentially OCaml's way of encoding existentials, so somewhat equivalent signatures like this, for those that are unfamiliar. Now note that key.create returns a key that's unique, and the uniqueness is also going to guarantee that it's fresh. Right. Now next, once a key is created, you can put data into the capsule by calling data.create. So data.create takes a constructor as an argument, and it creates data into any capsule. Now, most importantly, this constructor must be a portable function. And this is crucial. Right? So if we remember, non-portable function or functions that capture mutable values must be non-portable. So that means if a function is portable, it does not capture mutable references. And what this really means is that by being portable, it's impossible to create external aliases. This is going to guarantee that the environment is truly encapsulated. Note, however, there are no other restrictions. Okay, so, and indeed, data.create can run in parallel in multiple threads. This is fine since we're adding new data into the capsule. But this would not be fine if we're mutating existing data within the capsule. Right, so let's see how that's done. It's going to be done via a function called data.map. And the idea is to mutate the contents of a capsule, you were going to need the key uniquely. Okay, so let's go through it step by step. The key is required uniquely to be able to mutate. We then take a map function. It must be portable again. We then have a data.t from this particular capsule. Note the K is match. It then runs the function, returns the key uniquely, and the new data. Okay. So this is great. The uniqueness of the key will guarantee only one thread can mutate the capsule at any one time. However, what's missing now is the actual synchronization of the key. Right? We want multiple threads to get the key. And this is going to be handled by the mutex API. Note that in the paper, we present a more general reader-writer lock API, but for simplicity, I'm just going to stick to the mutex API. All right, so the key is going to be synchronized between threads with a mutex. To create a mutex, you consume the key uniquely. Right? So here the key goes into the mutex. And next, it can be acquired by calling mutex.protect. This works like a regular mutex acquiring as long as the function that you then run takes the key uniquely and returns it at the end. Okay. All right, this is all the ingredients we need. Let's use it in our example. So we're going to first create a key, put it into a mutex, and finally, we're going to allocate our queue by using data.create. Next, we're going to share this C between two threads, and they're going to run concurrently. And what's going to happen, they're both going to try to acquire the mutex. So let's, for example, say we are the second thread. They call mutex.protect. They happen to be able to acquire the key, which means they are now, the other thread is now waiting. They then call data.map with this unique key, to mutate the queue. And once they're done, they release K, and they relinquish it, and the mutex is closed. Now note that all of these functions, q.create, q.map, are really just mostly the original q module from OCaml. Okay. The only difference, or the only obligation, is that the q module must be annotated and recompiled so that all of the functions are portable. Okay, note that this is not a technical restriction. It's really like a key restriction here. It's very important that the queue doesn't create external aliases or anything that might break data rest freedom. Okay. However, if everything goes through, right, if the annotations go and the type checker works, well, nothing else needs to be done, and we did not need to be implemented. So in conclusion, I've presented DRFcaml. It's an extension of OXCaml that guarantees data rest freedom with 2 new axes, contention and portability. I then presented 2 APIs, the capsule API and the mutex API, that will allow us to safely share data structures between threads. And finally, there's also a lot of things that I've omitted. So in the paper, you can also read about the full design. So in particular, I want to call attention to a mode that I didn't present here, part of the contention access that allows us to share, to read share between threads, so multiple concurrent readers. Of course, you can also get the complete APIs, the full presentation of the type system, and also details about the mechanized formalization in Rocq and Iris. Okay. But for now, I'm very happy to take questions. Thank you.
Okay, we have a few questions. Let's start.
Hey, thanks for the talk. I was wondering if your key and data and mutex modules, are they typed by just, are you able to type them within your type system, or is magic involved?
No, the magic is involved, and part of the formalization is indeed to show that they are semantically type sound. Yeah, good question.
We have another question here.
This is really exciting work. I'm really curious if, so at the moment it seems like it probably doesn't affect the actual implementation of the language itself, it's more of just a type system feature. But I'm curious if you kind of along the way discovered opportunities to take advantage of this type system to improve the performance of concurrent code or parallel code that you might write with it.
So I cannot speak for the contention and portability per se. I know that the other modes did indeed, and part of the motivation was also to improve performance. So they actually influenced the backend of the compiler. As far as I know, portability and contention doesn't influence the implementation of the backend. The key focus was to guarantee data rest freedom for now.
Thank you.
It doesn't work.
Thank you. That was really nice work. So one question I've got is, how do you get data out of a capsule? So like you've got, say, a queue of integers, and it's in a capsule. Like, how do you get an int out of that?
Right. So you could destroy the capsule by consuming the key uniquely. This doesn't work if it's in the mutex, because it requires the key back. But if you could destroy everything, then yes, like if you could destroy the mutex and then destroy the key, then you can get data out. Yeah. But you can only get the data out that you're applying it to, right? And you could have like multiple views into your capsule, so you need to be a bit careful.
Okay, thank you.
Okay, we have time for one last question while I have the next speaker setting up, please.
Thank you. Thank you. So I was wondering, if I understood correctly, the mutex API is tied to this key type.
The one I presented
which
here, yeah.
I find it at first sight a bit surprising. So is this a fundamental limitation, or could this be a mutex that wraps any type like we do it in Rust, or would that just not be useful for some reason in OCaml?
Oh, okay. This is a really good question. I think it deserves a longer answer, but the short answer, yes,
Happy
you
to
could.
chat later.
Yeah, but you could do a more general mutex API. Actually, the one we prove in the semantic soundness is slightly more general. But the problem is, because it requires something uniquely, you don't necessarily have like deep uniqueness per se. If you have different nested references, you need to be a bit careful about which types you apply it to.
Okay, that makes sense. Thanks.
Okay, let's thank the speaker again.